at cell potential. Hello, my name is Scott Simpson, and today we'll be talking about the Nerst equation. The Nerst equation is an equation that you can use to look at cell potentials or the electromotive force under non-standard conditions. The electromotive force, or the EMF, depends on delta G. So let's relate delta G to the electromotive force. We're going to give the symbol E for the electromotive force. So we can start with the equation delta G at some other point, not at standard conditions, is equal to delta G naught under standard conditions plus R T, the natural log of Q. And what the natural log of Q is our reaction quotient. Okay, we also know that delta G is equal to the maximum work that you can get out of, there we go, let's try and make this a little brighter. The maximum work you can get out of chemical reaction, Wm max, which we know is also related to the negative moles that are transferred times Faraday's constant times E of the potential for the cell that we're looking at. So what we're going to do is we're going to utilize this expression over here. See if this will work. Yeah, we gotta wait a little bit. We're going to utilize this expression. You can do it. Let this ink sink in. Sorry, we gotta let that go. And we're going to plug it into this equation on that side. So let's prime and pump this tube. Now, all right. So let's plug in for this. So we get negative for moles, Faraday's constant, times the cell electromotive force is equal to, so since we have this G naught, we have to utilize that. So we have, all that's going to change in our expression is we're going to move from E to E naught, so negative N F E naught for our cell potential plus R T ln Q. We're going to keep that. Okay, so what we can do is we can manipulate this through. We want to try and find this electromotive force here at non-standard conditions. So what we're going to do is divide by negative NF. And when we do that, we get E is equal to E naught minus RT over NF times ln Q, our reaction quotient. Okay, now, as we're going through this, we can assume if we're at 25 degrees C, this reaction, this is a conglomeration of constants, we're going to get a new expression. So at 25 degrees C, this just changes to E naught minus 0.0592 divided by the moles of electrons that are transferred times log, notice the ln switched, of Q. So we can utilize this relationship to solve for different things. If we want to know a cell's potential at non-standard conditions, we can do that. If we want to know what the concentrations are, given we have some potential we measure, we know what E naught should be, we can actually solve for Q. So let's look at an example utilizing this. Oh, the board's moving on. Sorry about that. Let's lock that into place. Okay. Sorry, that was a little bit harder to clean than I thought it would be. Okay. So let's look at an example. Yeah. Consider the following battery, where we have solid zinc plus 2H plus aqueous goes to zinc 2 plus, and then hydrogen gas. The cell potential is found to be 0.54 volts positive. Oops. At 25 degrees to make our lives easier. We want to determine the H plus concentration if the concentration of our zinc 2 plus is equal to 2.5 molar, and the partial pressure for H2 is equal to 1.0 AT. So we have this as our problem. Okay, what are we looking for in this problem? We want to determine delta H, or I mean, excuse me, not delta H, the H plus ion concentration. The information that's important to us. We're told this aspect. We're told that the cell potential is found to be positive 0.25 at 25 degrees C, and we need to consider this reaction. Okay, since we're talking about non-standard conditions, this is where we want to use the Nerst equation. We have E is equal to E naught minus, since we're at 25 degrees C, 0.0592 divided by the number of moles of electrons transferred times log of our reaction quotient. Okay, now remember, our reaction quotient is just what our equilibrium constant is with initial conditions. Let me erase some of this while we have time. So what we need to do is we need to come up with an equilibrium expression. Kc, Keq. In this case, we have to look at our reaction. Remember, it's always products over reactants, and we have to exclude pure solids and pure liquids. In this case, we have a pure solid, zinc. We're going to exclude that guy. The rest we're going to utilize. So we have our products, concentration of zinc 2 plus. Then, since we're at a heterogeneous equilibrium, we're going to use the partial pressure of H2 because this is a gas that will be more convenient. And we're going to divide that by H plus squared. Okay, so this will be equal to our Q at initial conditions. So we have an expression for this. We are told these two values. So what we need to do is manipulate this equation around to solve for log Q. In order to do that, we're going to move E naught over. So we get E minus E naught is equal to negative 0.0592 divided by n. And we have that log of Q. Next, we're going to move this bit over. So let's do that. What's going to happen is if we move that negative over, we can flip this. Divided by 0.0592, multiply that by 10, and that's equal to our log of Q. And that's where we'll leave it for now until we solve this other question. Okay, so for Q, we're told that information, we'll utilize that later. We know that just being told that our E is equal to 0.54 volts. What we have to do now is figure out our E. So in order to do that, what we have to do is break our reaction into two half reactions. And we can do that. Another important point, note, this is at the general chemistry level. If you're going to an upper level course, this will have to change to something called activity. But if you're in general chemistry, I wouldn't really think about that right now. So now we would need to break this guy apart into two half reactions. We concern ourselves with the zinc 2+ aqueous, and then we have 2H+ aqueous going to H2 gas. Okay, given this information, what we have to try and find out is this an oxidation or a reduction? That first one. We're going from a 0 oxidation state to a 2+ oxidation state. That means we have to be giving off 2 electrons. In this case, that is showing an oxidation. The other, we're going from 2+ to a 0, that's showing a reduction. Therefore, we need 2 electrons on this side. Based upon that, you can look for the E0 of these reactions. The bottom one's pretty easy. This, by definition, is actually set to be 0 volts. That's a complete number, a direct number that has a large number of sig figs. This one we would have to look up. The value is positive 0.76 volts from the reference ion. Okay, in order to find this, what we have to do is sum these. Depending on how you like to define this, you can subtract them from one another. By flipping signs, I generally change the sign of these, but in this case, this is 0. So E0 for our cell is just the summation of these two things, so positive 0.76 volts. Okay, so now we have this information. We have our E0, which is 0.76. We're going to subtract off that 0.54 volts. We're going to divide by 0.0592. And then our N is the number of electrons transferred. In this case, it's 2. So times 2 is equal to log of Q. Now, if we solve for that, manipulating everything through, Q ends up being, actually, we'll do the log of Q. Log of Q ends up being 7.432. Okay. So now what we have to do is we have to do the anti-log to solve for Q. Sorry, just taking me a minute to erase. Feels very different than a chalkboard. Hard to see all those little spots too. So now we're at this guy. To do the anti-log, we just have to raise it to the power of 10. So we get Q is equal to 10 to 7.432. And when we manipulate that through, remember, we can use our equilibrium constant, but their initial conditions. This should be equal to zinc 2+ concentration initial, the partial pressure of H2 over the concentration of H plus squared. We're trying to find this H plus squared. We have values for this guy. If you look back at when we introduced this, it's 2.5 molar, and this partial pressure is 1.0 atm. So let's plug those values in. Let's solve for H. H plus is going to be equal to, so we're moving these guys around. Q, zinc 2 plus, partial pressure H2, and we got to take the square root of that or raise it to the 1/2 power. Now with doing that, we just have to plug in all of our values. So 2.5 times 1.0 divided by 10 to the 7.432. And after everything is said and done, we get a value of 3.0 times 10 to the minus. So here we've given an example of how to utilize the Nerst equation to solve for something that is not at standard conditions, where everything is at 1 atmosphere, 1 molar. In this case, this is what we arrived at by manipulating the Nerst equation. So thank you very much for listening. If you have any questions or comments, please leave them below. Thank you.